First of all, thank you very much for your invitation. It's really a pleasure to be here with you today. I'm Mario Pereira. I'm a researcher and a market history fellow at Nova School of Science and Technology and the associated Nova Links Lab, which is a university and a research laboratory for computer science in Portugal, Lisbon, the capital. This is joint work with Antonio Bavaro, which is also a professor and a researcher there. And what I'm going to present you today is our work on Cameleer, a deductive verification tool for OCaml. So, put this on full screen. So maybe you have heard about the Tezos blockchain, which is developed using the OCaml language. And so last October, Arthur Breitman, the founder of the Tezos Foundation, the creator of the blockchain itself, who is also a seasoned OCaml programmer, posted this very simple puzzle on the public Tezos the developers Slack. Okay, and so the idea was to write a very simple program which would compute imperatively the sum of the first elements of an array until you reach the first negative value in that same array. Okay, and so he posted this simple code snippet, and he immediately told that he could not prove this assertion here. And so why was that? Okay, because the code apparently is very simple, and so it should be doing what was supposed to be doing. Okay, well, maybe, or I expect that the attentive OCaml programmer would immediately spot the bug, and it comes maybe from, or it was maybe written by someone with a kind of more expertise with imperative programmer. Why? Because actually the person who wrote this code was thinking about using the bang operator here as a negation operator, which is not true in OCaml, and so this program was not correct because of that. But what if we try to formally verify this puzzle? I mean, in a way to show that this program, or to formally show that this program is not correct, and maybe try to come up with a better solution, with a sound solution, and at the same time formally verify or mechanically prove that the new implementation is correct. So the recipe would be first to prove safety. I mean that every access to the array in the implementation is done within bounds. All right, that the program also terminates, and that would be the safety of your program. And finally, you would may be interested to prove functional correctness, which means that at the end of the loop, or at the end of the function, you actually got the sum of all non-negative elements in the array, of the prefix of non-negative elements in that array. Okay, so let's try to do this first on a more pen and paper approach. Let's imagine that we have a specification language for OCaml. So what would look like, or what would be the effort to try to come up with a proof of correctness for this program? What would one have to do? So you would need to first and foremost provide an invariant, okay, which would say that, okay, during the executions of this while loop, the index iter.i is always within bounds of the array. Maybe it would be equal to array length of a at the very last iteration. So in particular, you would know that this access to the array would be safe. Okay. Well, the problem is that this is not a good invariant. Okay, you can convince yourself by some manual effort that this is actually not a very good, or this is not an invariant at all. Well, because imagine that in the first place you have an array that is all filled with non-negative elements. So in that case, you will just loop forever. Okay, and so at some point you would lose the safety of this access here. Okay, so this is not a good invariant, or at least I cannot use it as an invariant at this point. Okay, so let's go for the second attempt. And now I'm also imagining that I put a precondition on my OCaml code. Okay, and this precondition, which I introduced with this hypothetical requires, says that, okay, at some point there is an index within the array limits that says, okay, from now on, okay, everybody is less than, or at this point, the element I is a negative element. Okay, so this marks the point where I'm going to start to have only negative elements in my array. Okay, and so now I can provide a sort of a new invariant, one that says that, okay, I always have a bound, okay, for my iter.i index. Okay, and in this case, since j is well in bounds of the array, this access here is safe. So maybe we are on a good track to try to prove the program given this new precondition. Okay, so now as we are interested in safety, the second part of safety would be to prove that this loop does not diverge. And so what I do is I would provide a decreasing measure in the form of a variant. Okay, and since iter.i is growing, maybe I would like to use it as a variant here. So I say that the value of array length of a minus iter.i is strictly decreasing, but I need to account for the fact or for the case where it's not anymore the case where iter.i increases. Okay, because in the else branch it is the case that iter.i increases but not on the dead branch. So what I do is that I add here a kind of measure to when the value of finish flips. Okay, and so this auxiliary function int of bool is just it just has the expected semantics. Okay, when finished is true, it returns 1, it returns 0 otherwise. Okay, well, the problem is that actually from the point of view of the loop, when you are already inside the loop, the finished value will never flip, because if you got into the loop, it was because finished was already true. So even if I can provide an invariant, okay, I cannot provide a variant, okay, or I cannot prove that this function terminates. Okay, so let's go for a final and a third and final attempt, right? Okay, and so what I'm going to say here now is that first and foremost, I'm going to specify the form of my array or the shape of my array. Okay, sorry. And so I'm going to introduce an auxiliary logical predicate, which says that either my array only contains non-negative values, or there is a point, an index within the array, where I'm going to name it I here. Okay, and before I, every value is non-negative, and after I, everybody is a negative element. Okay, so I call this the negative array property, and I'm going to use it as a precondition of my array A, right? And so next, I introduce the post condition, okay, to say that, okay, at the end of my sum until negative function, I would like for the R result, which I'm giving here a name to the result of this computation, right? And so let us imagine that we have a logic sum function, which is a logical function that captures the summation operator, okay? And this is parameterized by a lambda term, which says that, okay, if my value within the array, that means in the index I, is negative, then I'm not putting on the summation. Okay, otherwise I'll just return it, and it's the normal summation. Okay, and this happens from 0 inclusive to the length of the array exclusively. All right, and so with this contract here and this predicate negative array, I might expect to prove my program. Okay, So in this case, I'm not going to use the finished variable anymore, and now I'm trying to prove it, and at the same time giving a better implementation, a more idiomatic implementation of that bogus program that we saw before. So I'm introducing a local exception finished, okay? And the test from my while loop, what I'm saying is that I'm going to iterate until the value of iter.I is strictly less than the length of the array. And in the code of the loop, the only change is that now if I get to find a negative value, I immediately raise finished with the current value of iter.sum, of course. And at the end, all right, so if I ever raised my finish exception, I just return the argument that was carried along with the exception, right? And so now I can start providing specification elements. Okay, now it's much easier to prove termination, which now amounts to a simple difference between the length of the array and the value of iter.I. As to the invariant properties, I can now prove that this index iter.I is always within bounds. Okay, that for every element that I have of the array that I have traversed so far, every element is non-negative. Okay, this is important to prove the post condition. And finally, that the value of sum, okay, at any point during any iteration, actually is or it can be modeled by the application of the logic sum function, but now the range is restricted to iter.I, which will be all we need to prove the post condition when, for instance, iter.I reaches exactly the length of the array. And so this is good, okay? I've written a bunch of specification, which is actually valid specification in the sense that allows me to prove that the implementation corresponds or is correct with respect to that very same specification. Well, but the fact is that, okay, this exercise was very fun to do by hand, but what I would like is for us to have a tool for the OCaml programmer to check this proof. I mean, to mechanically check this proof. Is there any such tool? No, or better said, there was no such tool before the time of this talk, which is kind of puzzling because deductive verification has been seldom applied to the functional world, right? There is a lot of work about proof of imperative programs, but much less about proof of functional programming. As I was saying, this is puzzling because if we think about the features of OCaml, this is a language with a clear syntax. I mean, most of the time it has a clear syntax. It features a well-defined execution model, to say operational semantics. And it's a multi-paradigm language which combines imperative programming, functional programming, object-oriented programming, which allows someone to write very concise and type-safe code, which most of the times is the key to achieve a correct implementation. And moreover, OCaml is the language of choice to implement one can call sensitive software. I mean, software where correctness is of utmost importance, like the cogproof assistant, the pharmacy, software analyzing tool set, very fast program, the very fast, which is a framework for the verification of Java and C code, the infer tool, which is used at Facebook, and a bunch of other verification tools, but also tools that are used or software that is used on industrial context, like the Mirage operating system, the Docker container management system, the Messenger client, and also, of course, the Tezos blockchain. So it would be of interest to have a tool for the formal verification of OCaml-written code. So that's how the Cameleer project was born. Okay, Cameleer is a project that is in the scope of an individual Marie Curie fellowship, which started last June. Okay, Cameleer is now 1 year old. Okay, it will actually be tomorrow 1 year old, and it will run until next May. Okay, and so what we are aiming here is to build the first automated tool for the verification of annotated OCaml program. One key ingredient of our research agenda and tool development agenda is the use of Gospel. And here Gospel stands for generic OCaml specification language. I'll show you more in details what is Gospel in just a few moments. Okay, we have chosen to tackle the Cameleer project and to build these verification tools in 3 steps. First, we'll tackle bounded mutability programs using the Y3 framework, which means that we are going to take an OCaml program and translate it into the Y3 verification framework. Okay, and here bounded mutability means that we cannot do things like recursive mutable data structures, or in other words, we cannot deal with arbitrary pointers manipulation or memory aliasing. And when we'll move to it, or when we really want to deal with that class of programs, now we'll turn into the Viper infrastructure, which is an intermediate verification language based on a form of separation logic that also allows you to do some kind of automated proof. And at the end of the project, when we are really into proving higher order effectful programs, okay, I mean, kind of arbitrary OCaml programs where you mix high order with arbitrary effects, at that point, we'll need to turn ourselves into a much richer tool and much more expressive tool like the CFML toolchain, which builds on separation logic encoding inside the code proof assistant. So today, I'm going to talk to you a little bit about where we are on this translation into the Y3 system. Our roadmap in terms of research expectation, well, we really want to build specification using Gospel that OCaml programmers can read and even write, because we really believe on the vision of the specifying programmer. I mean, the person that wrote the code should be also able to write specification for it. We want Cameleer to use a proof assistant, but somehow abstract it to the end user as much as possible, right? And most importantly, I think we really want to focus on proof automation, because we believe that proof or interactive based tools are hardly going to be the choice of any regular OCaml program. And finally, we want to keep evolving the Gospel language and make it into a much more mature proof language. In this talk, I'll be showing you two aspects of this research agenda. First, I'll briefly describe the Gospel specification language and its design choices. And finally, I'll mostly focus on how to use the Cameleer tool to actually deductively verify OCaml code. Okay, so imagine that you are an OCaml programmer, right? And you want to use a library that provides you with a queue data structure. So when you open the queue.mli file, what you'll see is most likely these 4 lines of OCaml code, right? So you know that you have access to a polymorphic data structure named T, and that over that data structure, you can perform 3 operations. You can create a new queue, you can push elements to that queue, and you can pop elements from the data structure, okay? But this is a pity, because you have no information about the semantics, the behavior of your data structure and functions. So if you are lucky enough, currently what you see on OCaml libraries is this form of informal comments or natural language comments, right? So yeah, okay, if you trust these kind of comments, you know that, for instance, whenever you call push, yeah, the elements are appended to the end of the queue, and when you pop, you remove from the head. Okay, it gives you some kind of semantics behind this function, but it's not very rigorous. Okay, it's not rigorously defined, and it's something that you can trust. Okay. So what we seek is that maybe we can, for instance, use separation logic to give the specification elements to these data structures, okay? Because you could almost suspect that this was going to be an imperative data structure because of all these units when you create and when you push. But now with separation logic, we can say much more precise things like, okay, my data structure is equipped with a representation predicate called R, and then I'm going to use this representation predicate to say things like, by the way, this representation predicate means that you always have a well-formed queue data structure in your memory, right? In your heap memory, and you can use it, for instance, when you create to say, okay, I return a new well-formed queue given by this representation predicate, where capital L means the logical model of the elements inside the queue. And this is a list, and it's a logical list. So that's why here we say that this is a nil list, right? So it's empty. When you create it, it's empty, it contains no elements. But now when you push, you sort of update your model, right? You append to the end, to the very end of your model, a new element v, which was the argument that you passed to the function push, right? So we are here also naming the arguments of every function, right? And when you pop, okay, the previous model was actually the concatenation of v to the new model. Well, the thing is that I was talking about specification that the regular OCaml programmer can read and even write. Well, I'm not even sure that regular OCaml programmers can read the specification, the separation logic specification, and I'm almost positive that they cannot write it. So here's where gospel comes into scene, right? So instead of giving all these very complicated separation logic elements, we try to put into place a specification language that is much easier to use, but at the same time as expressive as separation logic. So instead of a representation predicate, what we attach to the definition of this type of the data structure is a model, okay, which is still a logical list, and we say that you can mutate the model in place, so that's why we use the mutable keyword. Okay. Now, when it comes to function contracts, things are much more simplified, I believe. Now, you say as a post condition that your model is the empty list. Okay. Here you are even using OCaml syntax, which is nice. So we want gospel terms to be written in a subset of the OCaml language itself to be easier for OCaml programmers, right? And now, when it comes to do some sort of side effects to the data structure, we can state it very clear. So this is kind of very rigorous documentation to the OCaml programmer that is using this data structure. The modifies queue here states that it's going to happen a side effect on the data structure. And your post condition now, again, is stated in terms of the logical model of the data structure, which is kind of the only way you have to reason about the data structure here. Okay, and finally, here on the pop function, I have another element of very precise documentation, which specifically says as a precondition that I can only rely on my pop function whenever I give it a non-empty queue data structure. Okay. Which is really good, because now I can for sure know that this is only usable in certain conditions, and I don't need to pose myself the question to know when to use or not the pop that is provided in the library. Yeah, just a quick word to say that this old keyword is talking about the value of queue.view on the pre-state. I mean, before executing the push and pop function. Okay, so the gospel specification language should be expressive. I I mean, user right specification in an extension of first order logic, understandable by OCaml programmers. Okay, as I said, gospel terms are written in a subset of OCaml. Concise, which is a which is a greater improvement over separation logic. And a very, very interesting feature is that it is not tied to any particular verification tool. Okay, we have designed gospel with no verification tool in mind. It behaves a little bit like GML for Java or ACSL for the C language. But we care about giving the gospel a formal semantics, and this formal semantics is given in terms of the translation into regular separation logic. Okay. For more details, I invite you to read our paper that was presented on last symposium on formal methods, which was in 2019 at Porto. Okay, so I'll give you a quick tour around gospel features now. So still on the example of the queue data structure, now imagine that you want to specify or introduce an emptiness test function, which I call is empty. Well, in this case, you're going to return a boolean, which we name b, and this boolean is true if and only if the view is the empty list. Okay, I could have replaced it here with some syntactic sugar. Okay, I agree. But in terms, what is important here is that we can provide a translation into the following separation logic triple. Okay, let's first look into the post condition. Okay, the post condition is a function. Okay, that's why I use here the lambda to give a name to the result. Okay, and this post condition is only going to assert a pure predicate. I mean, the post condition does not assert anything about the heap memory. Okay, in particular, is only going to assert that again, B is only true if and only if the model is empty. So now back to the precondition. Here, what we are using this RO permission, it's what we call a temporary read-only permission, right? Because you are not going to change the queue argument, so kind of you only use it to reading access. So no need to worry about side effects on queue inside your proof. So we use these read-only temporary read-only permissions introduced by Charquerot and Poitier on their ESOP 17 paper. Okay, and so this is only usable, these RO predicate inside preconditions. These are implicitly returning post conditions, so you still get your representation predicate at the end of this empty function. And any read-write permissions can be locally turned into RO permissions, so it's kind of a scope-based permission. Okay. One important note, just to say that this is not syntactic sugar. There is a definition in the paper by Arthur and François that this is a new kind of separation logic framework. Okay, one where these RO predicates are part of the definition of the rules themselves. Okay, but this is really very usable or useful when you are doing read-only proofs. Now let's go into a more separation logic-like thing. Which is, yeah, any questions?
Mario, we will ask questions on the go. Yes.
Oh yeah, for sure.
Can you roll back one slide?
Yeah.
You said that if is empty is pure function something.
Yeah.
How translation to separation logic can know that is empty is empty is pure indeed, or maybe something else?
Okay. Yeah. Thank you very much for the question. If you allow me, the answer is right here on the next slide, because here I employ the modifies clause. Okay. So if I come back, there is no modifies. So in gospel, we assume that when, remember, this is an interface file. If you do not put any modifies on the function contract, okay, so it is a pure function. I mean a side-free effect function. Okay, so in this case, it's not going to be like that. Does that answer your question?
Yeah, I just need to look at special syntax. It seems like the keyword modifiers is about it.
Sorry?
The keyword modifiers is about this mutability specification.
Yes. Yeah, that's correct. Yeah. So in this case, you are specifying that you are saying that inside in-place concat there is going to be some side effects performed over the arguments q1 and q2. Okay. And in this case, what I'm doing is that I'm doing an in-place concat where I'm going to empty or clearing the first queue, but I'm not going to lose possession over it. Okay, I'm going to at the end of this function, I still can perform operations on it afterwards, or in another sentence, I do not lose possession of the pointer. Okay, which is kind of a big deal when you are using separation logic. And finally, the queue view is now updated accordingly. So I mean that you append all the elements from the previous view of Q1 to the end of the elements of the previous elements in Q2. And so you build the new view for Q2. Okay? Is there any question? I kind of heard.
Yeah. Mario, so how do you actually enforce that modifies actually corresponds to a side effect free function?
But I think you are already thinking about implementation. Okay, yeah. So in this case, I'm only focusing about the specification of interface files. When we come to implementation, in particular, when I'm using Y3, the Y3 type system will actually check that these modifies effects happen there.
Okay, thanks.
Okay, so yeah, keep in mind that for now, this is only interface files. So you, as a programmer, you are saying that these effects will happen, but so far, no code, no implementation. So you cannot see for sure these effects happening. Okay, so.
And one more question. On a few slides ago, you described the view, the logical representation of your queue to be a list.
Yes.
This list is this type list a pre-built list or some other list, or you implicitly add all data types declared in your program to be used in Gospel or something else? I'm worried that for real big programs, you will need to invent some complex view types which can be not present in actual code without all annotations.
Yeah, so I agree with you. So in this case, you could use lists from the OCaml standard library, okay? But imagine that now you need more complex logical data types like sets, bags, sequences, and so on and so on. And for that, we provide with Gospel a comprehensive standard library of specification elements where we are putting an effort to gather a quite large number of specification data structures, sets, bags, sequences, and so on and so on. But imagine, I agree with you, that somehow you need a different data type to specify your real data structure. In that case, you need to supply it as in Gospel comments. Okay, you need to write it inside Gospel elements to be able to use it. But the more common patterns, I think they are covered by the Gospel standard library.
Okay, thanks.
Yeah. So just to finish this slide, when we are translating this specification, Gospel specification into separation logic, in this case, it's very classic because you say that you have two separated data structures, well represented Q data structures, and at the end in the post condition, you still get two well-represented Q data structures with the same pointers. So Q1 and Q2 here stand for pointers, right? You are just updating their logical model, which now are L1 prime and L2 prime. Now, more interesting, let's imagine that we want to destroy Q1, okay? So let's imagine that you just want to give Q1 to the garbage collector of the OCaml compiler. Right? So in that case, gospel provides you with a consumes clause, and in this case you are saying that the in-place destructive concat function is going to leave Q1 to the garbage collector, so you no longer have possession of Q1 after executing the in-place destructive concat. And in that case, you still put Q2 on the modifies, right? Well, but in that case, you only, in your post condition, you can only access old Q1.view. Okay, so gospel will emit an error if you ever try to access Q1.view inside the post condition when you already have put Q1 on the consumes clause, right? So in terms of translation into separation logic, as you can see, on your post condition, you only have possession of Q2, right? So you lost possession of Q1. Yeah, we can argue that this is some kind of memory leaking, but it's still fine in a language like OCaml or in some form of affine logic to lose possession of some pointers. So that's also covered by gospel. And finally, the last variant of concat, right, is one where you are going to build a fresh queue, Q3, by using the elements of Q1 and Q2. So in this case, you are going to allocate a new queue data structure, which means that since you have not put Q1 and Q2 inside either a consumes or a modifies clause, now again Q1 and Q2 are to be considered read-only arguments. So that's why we have in the precondition are two hard predicates, right? Okay, so note, maybe I forgot to say, but this is the separation logic star operator. Okay, so implicitly on your post condition, you get back Q1 and Q2, but now you also have a freshly allocated Q3, okay? And since it is bad practice in OCaml to allocate a data structure that has some form of aliasing with the arguments, implicitly in gospel, we assume that a freshly allocated element is always separated from its arguments or from the arguments of the function. It's actually a fresh data structure and a new data structure that is aliasing with nobody. Okay, so in generical terms,
Mario, wait. Why did you say it is a bad practice?
It's kind of a thumb rule for OCaml programmers. It's not formalized. It's something that the community adopted as bad practice to build a new data structure which has aliasing with previously data structure. Okay, a new data structure. I mean, you are saying you allocate, and at some point you have aliasing with previously existing data structure.
I just thinking that in this approach you will have difficulties to prove something about standard algorithms from pure functional data structures book, because aliasing is everywhere there.
Okay, you were talking about memory sharing. That's different somehow, because in that case, in purely data structure, you only have pure models. So I mean, when you change the model of your data structure, you are only change the model, the view of that data structure. So you are not thinking about, oh, maybe I can also change the view of some other data structure. Okay, because think about the logical model, right? And in purely functional data structure, even if they are alias in memory, it's not a problem, because your view will not be affected by that.
So it is not non-aliasing for logical representations, not for actual values of the queue.
Yes, that is correct. Yes.
Okay, thank you.
Okay. So in generic terms, imagine that we have an hypothetical code like this. I mean, this is put on an OCaml interface, a type with two models, a function f that takes a lot of arguments of type t and returns also arguments of type t, and you put a gospel specification like this. A precondition, some part of the arguments are on the modifies clause. In particular, here you say that you are only mutating the left field of P2, so the right field is not touched, and we can also specify that using gospel, right? And you consume P3, right? And you have, of course, a postcondition queue. So this arbitrary gospel specification is translated into this somehow unreadable separation logic triple. I'm not going to bother you with the details. It's just to show that we have provided this general translation scheme, right? But what I want to stress here is that we really believe, or we are really convinced that gospel improves readability and conciseness over writing directly separation logic triple. So we believe that gospel is a much better suited surface specification logic than separation logic itself. Okay? Right. So far, using gospel, where were we? Or how could one use gospel to verify OCaml code? Okay? So far, we had three tools that were able to use gospel to provide some form of certified OCaml program. First, Y3, which is a tool that uses first-order logic and weakest precondition calculus. I mean, it uses a VCGen to generate verification conditions of annotated programs and sends them to automated theorem provers, like SMT solvers, namely. And Y3 targets imperative programs with limited mutability, as I already said. Mutability, where you can always statically know every aliasing, which forbids you to use things like recursive mutable data structures. You also have the coq proof assistant, where you can build a proof and then extract it automatically into OCaml executable code. And when you are using coq, you are mainly targeting purely applicative programs. And finally, the CFML tool, which features a higher order embedding within coq and targets arbitrary pointer programs, including pointers with high order computation. Okay, so far, an important remark is that gospel was only used inside signature files, which means .mli files. And if you wanted to use gospel with Y3 or coq, you would still need to write your programming in the language, the programming language of Y3 or the programming language of coq, and then rely on code extraction, which means that if you have a large library that you want to formally verify, you would still need to rewrite that library inside these programming languages. Okay? But on the other hand, CFML takes as input an OCaml code, yes, but CFML is still an interactive verification tool, one that requires high expertise of users, so it's not, or we believe it's not the first choice of regular programmers. So that's how the Cameleer tool enters the scene, right? And so in Cameleer, instead of using Y3 as before, which means that I would write my program in the YML language and then extract it into OCaml or C, but for our purposes, we are focusing here only in OCaml code, right? So now what we are going to do is to use Y3 as an intermediate verification language. So we will take OCaml code annotated with gospel elements, and we're going to rely on the compiler itself, or more precisely on the PPX library, to automatically give us an AST produced by the compiler, so no need to rewrite the parser for OCaml code. And then given that AST, we're going to automatically translate that into an AST written in YML. Right, so your entering point is no longer YML, and now it's OCaml code annotated with gospel. And everything here should be automated. You only need to write the OCaml implementation and gospel specification. Okay, so let's take a quick overview of our translation. Right, so far we are only supporting one can call core OCaml, which mainly corresponds to the camel light incarnation, right? And with some form of functors, because functors are so pervasive in OCaml, so no way to build a verification tool for OCaml without a minimal support for functors. So at this point, we do not support objects, right? Neither GADTs, which is generalized algebraic data types, and polymorphic variants, so no support for that so far. That's future work. And also, we only have limited support for higher order functions. In this case, we only support higher order functions where the argument function is effect-free. This is both a limitation of Y3 and gospel. And of course, the mutability, which I have already talked a lot about. We have defined our translation as a set of inference rules, but today I want to give you an overview of this translation using some examples. All right. The first one is a very simple one, which is two mutually recursive functions. Maybe the first example of mutual recursive functions that everybody has seen, which is the even-odd testing, right? And so you give this gospel specification, right, in forms of preconditions, termination measures, and post-conditions for both even and odd implementations, right? So this is the OCaml code, and Cameleer will automatically translate into this YML program. Okay, here everything is very simple because the code is almost one by one. Okay, it's identically almost one by one. The big thing is that on the YML side, specification is part of the code itself, while here is only given in forms of comments, right? And an important note is that on the YML side, the let-rec construction is limited to functions, while on the OCaml you could write let-rec to build recursive values. So if you try to do that, Cameleer will say that it cannot translate that recursive value into YML, only recursive lambda terms. Okay, so now imagine that on the OCaml side, once again, you write an implementation of Fibonacci computation, and you write it as a recursive function, textbook definition, but you know that this is not a very efficient way to compute Fibonacci in real scenarios. So you say that this is a logic function, which means that you can use it inside specification. For instance, here in the post condition of fib main, this fib is the same. So you are actually calling the fib function, and you also tag it with ghost attribute to say that this should be erased before compilation. And this is also the case when you are writing your fib-ox function. The argument n here is only used to facilitate the proof and specification purpose, right? So this should be, once again, erased before compilation. So what does this give you on the YML side? Well, now you have a bunch of keywords on YML to represent this structure. In particular, the ghost keyword is part of YML definition, and the logical nature is given by function. So this very, very long signature, let-rec ghost function, stands for a function that you give some definition, okay? It is still a function that you can use inside logical context. I mean, you can use it inside, for instance, post conditions, but it is a ghost function, so it should not go into compiled code, okay? But I mean, just to show you that Cameleer allows you to write these annotations to give you a much, to give you more expressiveness at the time you are writing your OCaml code and specifying it. Okay, now perhaps more interesting, you can define invariants over your data structure. For instance, you want to specify the type of non-empty lists, right? So you wrap it around a record type, and for instance, if you have this function here, which is going to return you the head of a non-empty list, right? You know this is an unreachable case, right? Because by the invariant of the data structure itself, you know this cannot happen. So in particular, this means that the semantics of a type invariant says that you are assuming as a precondition the invariant of your L argument, right? So on the YML side, right, you now have the invariant as part of the code itself, but more important is that the assert false from the OCaml side is translated into the absurd construction on YML, which has exactly the same semantics as assert false in the OCaml side, because, well, assert false is already treated in a special way by the OCaml type checker, which means that this should be a keyword, this should be a single word, but, well, they are still treating the OCaml compiler is still treating assert false in a different way, instead of replacing it with a keyword, for instance, like absurd. But at least Cameleer knows how to take care of it. Now, the more interesting part of the translation, at least I believe it's more interesting, because now this is where the OCaml and YML language start to diverge a little bit between themselves. Because while in OCaml you have like a rich module system, right? You can define local modules, okay, using the module instruct keyword for namespacing and organization purposes, right? So for instance, suppose we are trying to define the multiplication operation using only additions, right? And you are also proving or stating a lemma that your mult function is commutative, right? Cameleer will generate on the YML side a scope, okay, which is the closer you get on Y3 to local modules, right? But scopes are not to be confused with local modules. These are just for namespace management. Okay, so in particular, while in OCaml code you can give modules as argument to other modules, that's not the case with YML. So I'm talking here about functors. So imagine that you have this OCaml functor here, which is pervasive on the OCaml standard library, a module, a functor make that takes another type as its argument. Okay, so this is a type. You define here a type which is equipped with a total pre-order relation, and you do a bunch of things using the type T and the compare function you get from the functor argument, right? So Cameleer will generate the following YML program. Okay, so it will generate a scope for the functor make, and inside this scope, we'll generate a second scope for the functor argument, okay? And everything inside this nested scope must be undefined elements. So no implementation for type T and no implementation for the function compare, okay? So after the definition of scope org, everything now is what was on the functor make. So now here you can have actual implementations. And so this translation scheme from OCaml functors into scopes, nested scopes on YML is actually the dual of YML extraction into OCaml, right? If in the first place you write your code in YML and then you want to translate it into executable OCaml code, you need to write or to follow this pattern in order for Y3 to know that you want to extract a functor. Okay. So now let me show.
Mario.
Yeah, sure. Go ahead.
How YML distinguishes argument of a functor from module inside another module?
Sorry, I didn't quite get your question. Could you repeat it?
I think if on OCaml we will create a module make, and in the module make create a submodule ort, it should be translated in the same text on the screen as when module ort is argument of a functor make.
Yeah.
It seems that you can't in all cases translate back to OCaml because you need to distinguish functor argument from module inside a module, because it obviously would become a module inside a module, and it doesn't say anywhere that ord should be converted back to an argument. I hope you get my question.
Yeah. I think I got it. So from the point of view of Cameleer, that's okay, because you are only proving things, and the code that you are actually going to put into production is the code that you wrote in the first place in OCaml. So it's not a big deal the way that you translate it under the hood to Y3, right? Because again, you are going to compile your OCaml program. Now, on the other hand, if you are writing everything from scratch on YML, in that case, you need to be much more attentive, because the Y3 or the YML module system is actually based on the mixins module system, and not on something like the more standard ML module system. Okay, so that's something that you should bear in mind, that when you are writing everything on YML, you know that you are in a context where the semantics of modules is much closer to mixins. But again, if you wrote in OCaml, it's fine to translate that way to Y3. I mean, you never know that it's a nested scope, right? So as long as you are able to do your proof, it's fine. You just need to be much more careful when writing everything from scratch on YML.
Okay, thanks.
Okay, let me try to show you a demo of how Cameleer works in practice using the examples of the queue data structure and the puzzle from Arthur Breitman. Okay, so now this is everything we saw on the slides about the queue data structure. Okay, so this is exactly the specification of the interface for the queue, right? So imagine that you wrap all of this information inside the module type queue, okay? And now you use this as a signature to an actual implementation of the queue data structure, right? So don't need to bother. This is exactly the gospel specification that was on the slides, okay? Really copy paste, okay? So now the actual interesting part is when I get into the implementation. So now you are starting to implement your queue data structure, right? And you are ascribing it the type queue. So I mean, your implementation must respect all the definitions that you promised me on this signature. All right. So okay. So now you are actually giving a type definition, not anymore a declaration. Now you are actually defining the type queue. So we are doing this in Baker style. So we have a front list, we have a rear list, right? And since we want a constant time or to know in constant time the number of elements of our queue, we also put here a field for the size. And this field here, this is actually very special because we are tagging it with ghost. Okay. So in this case, we know that this is only for specification and proving purposes. We attach an invariant to the actual type definition, one that says, okay, so size is always, this invariant must be always maintained by any inhabitant of the type T. So size is always equal to the length of view, right? And so for the front and rear lists, front is only empty if rear is always is also empty. So which means that at any point you can only empty front if you already have emptied rear. And this is to achieve amortized constant time operations. Now you put the elements on the front list on the correct order of insertion, but you put those in reverse order on the rear list, right? So you write your functions like create function, okay? The isEmpty function here, you know, okay, the one that everything is read only. So this is here. It's important to notice that I can write my, I don't need to write the modified clause here, sorry, and the Y3 type system itself, after translation, will actually know that no effect is happening here, so it's very nice to translate to Y3 at this phase. Okay, so maybe more importantly here is that here I should be writing the modified, right here, like the one I have here. But again, I don't need to do that here on the implementation side because I know that I'm going to translate into Y3. So Y3 itself alone will already check for every effect happening inside the push function. So in a minute, I'll show you the proof of refining, which means that this push here function we will need to prove that it refines this push here, in particular that every effect that is happening inside push is a valid effect, or in other words, an effect that I have already predicted. I'll show that in a minute. So again, these functions are okay, are simple. The pop function is a little bit more elaborated, but it's still okay. The more interesting one is the in-place concat. Okay, why? Because you need to provide more involved invariant here. In particular, for functional correctness, to prove the post condition, you need to assert that the current view of Q2 concatenated with the current view of Q1 at any point is equal to concatenating all the old view of Q2 to the elements or the old elements of Q1. Okay, so you are evolving your views at one iteration at a time. Okay, but you are maintaining the global property or the invariant property that at any point you are not losing elements nor gaining new elements. I mean, so all the elements that you are manipulating come from the Q1 views and the Q2 views. Okay, and so you also need to provide more structural invariants, like to say that, okay, you need to maintain by hand. This is a more elaborate, but it's because you are translating into Y3, right? Because Y3 alone will not detect that the type invariant that we provided here, is always true inside the loop that is changing, that is performing side effects on Q1 and Q2. Because here you are calling pop on Q1, so you are mutating Q1, and push on Q2, so you are also mutating Q2. So you need to replicate as a loop invariant the type invariance. Okay, so this is, but again, once you realize it, it's just copy paste the type invariant for Q1 and the type invariant for Q2. Okay. And the post condition is exactly the one that I've shown you in the slides. So now to do a proof using Cameleer, it is as easy as typing Cameleer and the name of the file, in this case ephemeral q, and it launches the Y3 IDE, sorry. Okay, so here on the right hand side, I have my original code. Okay, so this is the code that I've written, right? And on the left hand side, I have the proof tree generated by Y3. So let's forget about this refinement queue for a moment, and let's focus here on the things that are generated for the main module, the queue model itself. Okay, so you have here a verification condition for the data type T, right? And you can look into the task. Okay, so this is the formula that you need to prove. And in this case, well, you need to show that this invariant here is not introducing a contradiction in your context. In other words, you need to show that the type T equipped with this invariant has at least one inhabitant, right? So I can, for instance, go here and type AlterGo. I really like the XMT solver AlterGo, right? And you now see this green button here, okay? Which means that AlterGo was able to prove this verification condition. So you know for sure that type has at least one inhabitant. And I can actually see the time it took, and it was almost instantaneous. So this was a very easy proof for alter go, right? So if we continue on the proof, now we have the create function. Okay, so this is actually the representation for the verification conditions that are generated by Y3 for the create function. So once again, you can take a look into the formula that you need to prove. Okay, so this is a big formula. So you can I can press S on my keyboard, and the Y3 IDE is actually splitting into more simpler formulas. For instance, now I know I need to prove a precondition. Okay, which precondition it means the type invariant. Okay, the first line of the type invariant and the second line of the type invariant. And finally, the postcondition is the postcondition of the function create itself. So once again, now I choose this node here. I go into my interactive bar, I press Alt and Go, and everything is proved again almost instantaneously. So if I want to keep going with the isEmpty function, push, add list, and also the in-place, the more elaborated in-place concat, let me try to prove those at once. So once again, now I choose the old file, right? And now I typed alter go, and it gets everything proved almost instantaneously. Okay, so alter go is able to prove every verification condition generated for the functions that I have implemented and specified on the queue model. So now it comes to the refinement queue proof. Okay, and in this case, since I've said that okay, my queue implementation must respect the queue signature, so what Cameleer is generating is a form of refinement proof. And in this case, what I'm saying is that for the type T, okay, the type invariant must imply the type invariant of the implementation must imply the type invariant of the interface. There is none, so it's trivial, right? But for each function, the specification that I gave here on the implementation must imply the specification that I gave in the signature. In other words, or from a practical point of view, it means that the preconditions from the interface must imply the preconditions on the implementation, and the postconditions of the implementation must imply the postconditions on the interface. And so I think you all have already guessed, this is an instantiation of the consequence rule from OR logic, right? So most of the cases, this is trivial because, for instance, for the create function, okay, the specification in the implementation is exactly the same as the interface. So once again, I can look into my formula, but is exactly a trivial proof. So let's call alter go again. It's trivial. The isEmpty function, again, I think this is very, very simple because once again, it's the same one. So alter go again. Pop function, let me take a look. It's the same, I guess. Yeah, no need to worry. Okay, push, it's exactly the same one, except for the effects, right? As I said, in my signature, I need to explicitly state the effects that this function is performing. On the implementation, Y3 will take care of it. But once Cameleer says to Y3, okay, so I want to show that push here from the implementation is a refinement of the push of the signature, Y3 implicitly is going to check the effects from me, which means that all the effects of the push here from the implementation must be contained inside the effects that I have declared here. So that is the case. So alter go will have no problem showing this, and the same thing for the alter go, for the in-place concat function. Okay. So once I get everything green, I know that the program that Cameleer translated into YML, and you haven't seen any form of YML code so far, so you do not need to bother about the program that Cameleer is generating. You just need to know that that's happening, and on the Y3 IDE you can conduct a proof of correctness of your program, right? And also, let me show you how you can use batch mode. I think I can write it like this: batch. I can say prover alter go. Okay, so now what this is doing is that the proof was really simple, so maybe I don't even need to go into the Y3 graphical user interface. What I'm trying to here, what I'm doing is that I'm running Cameleer in batch mode, so you get a bunch of verification conditions that you try to prove all of those with alter go, and you see that everything is valid. So you prove and you get a green finished here. So you can also use Cameleer in batch mode, and in this case, you don't even know that Y3 is running on the background. Okay, the second demo is the puzzle, the one that we saw in the beginning by Breitman. Okay, and in this case, I'm going to need the Y3 graphical user interface, because that I need to do a little bit more than just calling alter go. Okay, so let me just say again, Cameleer puzzle. All right, so once again, here I am on the Y3 interactive proof session. All right, so here, what I see is that the first implementation is the one without any specification. So if I try to split it into the determination and safety conditions, no SMT solver. So I'm running all of the SMT solvers that I have installed on my machine. I just press 0 on my keyboard, and that makes to run them all in parallel, one by one. Okay, so nobody is able to prove any of these verification conditions, which is normal. I didn't supply any form of specification. The second implementation is the one where I gave the first invariant. So let me do a split here. Okay, and here I have a bunch of verification conditions. I'm going to press 0 again. Okay, I see that, yeah, with that invariant, I would be able to prove that index access to the arrays are done within bounds. Okay, in the case that I perform the then branch, the invariant would still be true, but not for the else branch where I increment my counter, right? And more dramatical is that this invariant is not even true in the first place before the first iteration. Okay, so that's what this loop invariant init means. So okay, so now we are convinced that this is not a very good specification. So let's move on to the third implementation and specification. This is the one where I've put the precondition that existed an index in the array with an element that is negative. Okay, so in this case I'm going to do a split again. Y3 has this odd behavior, but okay, let's go. Alter go. Okay, and now you see that alter go is not able to prove one of them, only one of them. Maybe I can try with CVC4 or Z3. This is a very, very nice feature of Y3 that you can interface with multiple SMT solvers, and I can tell you that that's a lifesaver when you're doing bigger proofs. You really want more than one SMT solver on your machine. But none of them are able to prove that this function actually finish or the loop is going to terminate when you do the then branch. Okay, so as I already told you, this was the case. And finally, let me go down a little bit. So this is the sum until -3 is the last version, the one where we have changed a little bit the implementation to use the local exception finish, and we have provided a good invariant to the loop, and we are also using the logic sum. So this one is going to be proved. But before, as I was telling you, I do provide now an axiomatization what is the summation. Okay. So an iterative summation between L and U. So I give two axioms, in fact. One that is the base case, the other one is the iterative or the inductive step, right? No need to bother with the details. This is actually very, very straightforward. And now I need to take care of proving a certain number of results about my logic sum function. For instance, that I can extend it to the left, right? Okay, so this is how I introduce a lemma using gospel specification, right? And so this is the lemma here. And you can see already that I've proved it already, right? But if you look more close, you can say, okay, but this is a lemma that you need to prove by induction. So how do you do it? Well, this is actually very easy by using the Y3 interactive proof session. I mean, you just write introduce premises in your interactive bar. Okay, so let me show you the task before. Now you have done introduce premises, so you introduce everything into the context. Okay, and now you are able to write induction B from A. So do induction on B starting from value A. Okay, so and Y3 is going to automatically generate a base case and a recursive case. And now in this setting, you are able to prove your lemma. So imagine that you try to do alter go here on the first place. You don't do induction. Okay, imagine that you try to do a proof before induction. So no lucky. I mean, it's no surprise you are not able to prove this lemma without induction. Okay, and then this is the same for every other lemma here. Okay, in my context. Okay, I'm doing here a lot of proofs by induction, as you can see. Let me hit here, sorry. Okay, okay. So you always see that I'm doing induction B from A, induction B, induction B, induction B, until I get to this one, to decomposition, which means that you can split your summation. All right, now you have three arguments, A, B, and C, and in this case, actually, I'm going to try to do this directly. I'm here trying to actually encode a lemma as a program, which is very useful if you want to do the proof by induction directly. Okay, let me try alter go. No luck. Okay, yeah, I think this one I have no lucky because I have not provided a proof, so it's not very, very interesting to write it this way, but just for showing you. So again, I need to do a proof by induction by hand myself. So I'm going to do introduce premises, and in this case, I know Y3 has this odd behavior of jumping around nodes, so don't bother with that. So now I know I need to do an induction. Okay, I'm writing yes, C from B. Okay, so now I want to perform induction on C, starting from value B. And I think alter go is now good to go. Yeah, so alter go is able to prove this after induction C from B. But here I also have a shift left property. Okay, and now I'm writing the lemma as a program. Okay, and I'm tagging it with the lemma attribute, which says that this is only a lemma, it's to be erased, it's not a program that you need to compile. Okay, and what I'm saying here is that if, okay, I can model the f function as a shift, okay, of the g function that I'm also giving as an argument, okay, the logic sum of f applied from A to B gives you the same value as applying g during your summation from C to D, okay? And so in this case, I've actually written the proof, the recursive proof as a program, okay? And so in this case, if I get here to the shift left on the here on the proof tree, I do a split. I see that I have a bunch of verification conditions like this was a regular program, variant decrease, precondition, and postcondition. I can call alter go, and so everything is green. So which means that you can also write your lemmas and prove them directly as a program. So which means that I could have already written every one of these lemmas and give them a direct proof. It almost feels like a little bit carry-out correspondence. Okay, so before jumping into the main implementation, I'm trying to now prove that when I call my good implementation on an array example, right? For this case, 1, 2, 3, 4, I will actually get 10 as my final result. Okay, so I'm going to prove main before proving the actual implementation. I'm doing a split. Okay, so here I'm going to tap 0 to see if any one of these guys is able to prove it. No, nobody is able to prove it. So let me try 0 before splitting. Okay, so nobody is able to prove it. Okay, so let me try to give them more time. Okay, because I only give them 1 second, and at the 1 second mark, they will all time out. So now I'm pressing 1, my keyword, my key 1. Let me check. I thought that CVC4 would be able to do this for a little bit more time. So this is the effect of live demo. Yeah, okay, so it was not CVC4, it was AlterGo with 1.02 seconds. It was almost there, but okay, so I also can state a little bit more for the timeout. I pressed 1, but you can also say, for instance, AlterGo space 5. So now you are giving 5 seconds of timeout to my SMT solver. So finally, to conclude, let's try to prove the actual implementation, the one that I've been announcing that is a good implementation. So I split it. I get a bunch of preconditions, verification conditions. Let me tap 0 to try to prove this with every available SMT solver. And the only thing that remains is, okay, the post condition. Yeah. So the post condition, when you raise, okay, when you are in the case that you raise finish, so you have kind of exited the loop before traversing all the arrays, so which means that you have reached the negative element. So this is actually a difficult post condition for automated SMT solvers. Okay. And so in this case, I need to help them a little bit. And now this is going to look a little bit like cock, because I need to do some form of interactive proofs, right? And I need to use the decomposition lemma here, okay? So I need to decompose my final summation, right? To say that I have a bunch of the array that is all non-negative elements and a bunch of the arrays where everything is non-negative. So what I'm saying here is that I need to instantiate this lemma here, the logic sum decomposition hypothesis. So I do instantiate, and let me check the name again, logic sum decomp, and I need to provide the lambda term. So this is why, or this is the thing that is making lives of SMT solvers very, very hard, is the use of lambda term. So in this case, it's actually very simple. So I'm just saying that this is exactly the same function, okay? Use the same function, or the same lambda term as in the post condition. The thing is that SMT solvers are not able to do that by themselves. They are not able to come up with smart lambda terms. So I say that if I is less than 0, just say 0, so no summation. And otherwise, it's a positive or a non-negative value, and just return it, okay, as is. Okay? And so, as you can see here, I have a new node, and I have a new hypothesis on my context, which is called hinst, okay, which resulted from instantiating my hypothesis with the lambda term. Okay, I can try to prove it now. Okay, let's see what my SMT solvers are able to do. No luck. Okay, I know that now I still need to go a little bit further, and I need to instantiate or give an instantiation to these 3 arguments. So I'm going to do instantiate inst with 0. Okay, so this is the value for A. Okay, it's the lower bound. The intermediate bound will be exactly iter.i. So this is the way Y3 writes things, but this is equivalent to writing iter.i, because that's where my loop traversal ended. Because remember, this is ending here. Okay, I'm stopping my loop before traversing all the array at this point. So I'm going to use it as an intermediate index. And finally, the last index is exactly the length of the array. All right. So now I have fully instantiated my hypothesis. Let's see, now that I typed AlterGo. Okay, no luck yet. Let me see with other SMT solvers. Let me tap 0. And CVC4 is actually very happy with this instantiation. So that's why I was saying that it's a lifesaver to have more than one SMT solver that you can use. And to the best of my knowledge, Y3 is the only framework that allows you to use more than one SMT solvers to conduct your proofs. Okay. So that was my demo. Back to the slides and to conclude my presentation. I have here a table, a very brief summary of some case studies that I have already been able to prove using Cameleer or the Cameleer toolchain, and then of course Y3 as we have seen. So far, the union find is the more interesting, or the most interesting example because it uses a very elegant and very sophisticated specification and is a 100% automated proof. Okay, even it's a very tricky data structure. And the largest example to date is a small arithmetic compiler that translates arithmetic expressions into a stack machine. Okay, to conclude, where are we now? So the road so far, we have built a deductive verification tool for a quite large subset of OCaml, a representative subset, and we have used it to verify several case studies, and most of them are automatically verified. And I mean, most of them is that sometimes I need to do a little bit of proof, of interactive proof, like we have seen for the puzzle example, but for me, it is still mostly automated proof. And I really appreciate the fact that the Y3 graphical user interface allows me to do this form of lightweight interactive proof, because I don't need to put those proof elements on my code. I can still translate them and then just to take care to put these very simple forms of interactive proof directly inside the graphical user interface. And when you are building a verification tool based on translation into a verification language, I really appreciate the fact that we can do that all on the Y3 side. As future work, I think it would be interesting to prove that our translation from OCaml to WhyML is sound, even if OCaml and WhyML are very close languages. From a more development point of view, we are already working on translating OCaml programs into Viper to tackle, in particular, the proof of and manipulation of recursive mutable data structures. And the final step would be to translate high-order effectful programs into CFML. At the end of the project, I believe by the end of next year, we want to have a tool that is able to take full advantage of 3 different intermediate verification languages, WhyML, Viper, and CFML, which means that we want to prove parts of an OCaml program with WhyML, other parts with Viper, and some very specific OCaml functions with CFML. And finally, the normal and the very regular question, when you are building a tool like this, can we already use Cameleer for even larger case studies? So far, we have a bunch of undergraduate projects of undergraduate students that are already using Cameleer to prove more realistic and industrial scale case studies, namely modules from the OCaml standard library and modules from libraries like OCaml Graph and containers, which are OCaml libraries that are widely used and used on an industrial setting. Okay, for more details, I invite you to read our paper that has just been accepted for presentation at this year's CAF, or even better, check out our Git repository on the link that I provide here. Okay, that's everything from me. Thank you very much for listening to me.
Thank you for your talk. Does anybody have any questions, comments, topics for discussion? Well, I'll ask a question.
Yeah.
in a table when you compare, when you presented the sizes of implementation and size of the specification, I saw that sometimes the specification is larger than the implementation. And this is the problem with both program verification, program synthesis domain, that it can turn out that writing specification is harder than writing a correct implementation. Can you comment on a little bit on this issue?
Yeah, for sure. So as you have stated very, very clear, I don't see this as a particular problem of Cameleer itself. It's more of a domain problem. Okay, let's take, for instance, this leftist heap implementation, because you can see that lines of code are only 68 and lines of specification is much, much larger. Okay, but in the end, the specification is very, very simple. Okay, everything is very standard. It's textbook definitions of what a heap must be. So my point of view on this question is that we need good specification libraries, and I mean specification and mathematical libraries that you can reuse, hopefully, across different tools. So I think that the community should try to do an effort to try to build good and reusable specification libraries to capture the specification, the purely mathematical specification of data structures. And for instance, I could use that library inside Cameleer, and so I would not need to rewrite my specification of a heap each time I'm doing another heap implementation, for instance. So I think that's my main concern about these issues, is that the community should really strike to have something that is reusable across different tools, and it would, quite significantly lower the specification effort, because if you have everything already reusable, you just need to import that library and you just need to put it on the right places, and no need to rewrite the specification yourself.
Yeah, I understand. Thank you. Any other questions?
Thank you, Mario.
Thank you.
I got the idea that your examples of programs are kind of not OCaml-ish enough. It seems to be very rarely people write while loops. It's rarely they put two values in a structure. More often they write a local recursive function and pass two arguments there and do explicit recursion in this function. Does all your Cameleer approach work if we don't write less obvious imperative programs, but more functional imperative programs?
Okay. That's an interesting question, because I was discussing that issue the other day with guys like Xavier Leroy and guys from the compiler itself, and what the conclusion is that we at the verification community have a tendency to show the very difficult things. I mean, and it's already very, very challenging and already very interesting to focus on purely applicative and purely functional programs, but we have a kind of tendency to show loops and to show quite difficult imperative data structures, right? So, and here I actually follow the same path, and I've shown you the more complicated aspects. But yes, I can still apply, and much easier. The results of the proof results using Cameleer to prove purely applicative programs like applicative queue. I'll show you in a minute, and other very elegant and very purely applicative implementation is much easier than writing while loops and arrays and so on and so on. So I would say that actually Cameleer applies or much better to purely applicative data structures. Let me just show you the one that I was talking about, which is actually an implementation of a queue data structure, but now in an applicative way, okay, which maybe is more Cameleer or Camel-like. Okay, so now here, so here you see that you still have the two lists, but now everything is pure. No effects, At each time you return a new queue. Each time you perform an operation on the queue, you return a new queue, and so on and so on. So yeah, the punchline is that I've shown you the difficult bits, but it's still very much amenable to the proof of purely applicative programming. It's even easier, much easier.
Do you need some special support of lazy values and not emulating call by need evaluation? It may be required for some data structures.
Yeah. For now, we have only focused on eager evaluation, if you want, or call by value evaluation. But we are considering proving the sec module from the OCaml standard library, which is kind of suspended list. But so far, no lazy data structure. We have not proven any lazy data structure, but that's very in our mind for future work. But again, that's something that OCaml programmers do not use that often, laziness. So we've pushed that into second place.
More questions?
Well, I have a question. Like these models, do you prove or suppose any algebraic structure on? Because, for example, these views remind me of the views framework in the CAP concurrent separation logic, and generally these models are usually assumed to be like separation algebras or partial component monoids.
Yeah, so no. For now, no special treatment of this kind of models. It's like a field of your record data type. So no. The answer is no. This is very regular fields and no kind of treatment like the iris separation logic is doing. No. But that would be interesting to take a more fundamental look into how these fields are behaving. And like proving, for instance, monotone properties and so on, automatically that would be nice, but so far we have done nothing of that.
Okay, thank you.
More questions?
Oh, thank you for a great talk.
Thank you for listening.
I have a small question. Maybe I have missed something. Which OCaml data types are you able to write as view specification? For example, you showed us view a list on your screen.
Yeah.
Which other algebraic data types I can use?
Okay, so that actually is contained. That for that we would need to look into the gospel standard library. But I'm also able to write things like sec, and this one is not to be confused with the sec from the OCaml standard library. Here is just a mathematical sequence. Okay, it's kind of an indexed list, but it's also a mathematical type. I can also write back, finite sets, and so on. So I would need to. I'm not sure how many and how and who. What are these model fields that I can provide? All of them at least, but I would need to look into the gospel standard library at this latest version. But what I can say is that you can still believe that you have pretty much everything that you might need. I mean, the normal mathematical data structures like sets, specs, sequences, and so on that you can find in the gospel standard library, and those are the ones that I support. So that said, if the gospel standard library evolves, Cameleer will also be able to consume those data types. Okay. Also, another source of inspiration is the Y3 standard library itself, where you have a very large collection of specification data structures, and all of those are replicated on the gospel standard library.
Thanks. So a user is limited to this standard library, and he cannot define his own.
Oh no, sorry. That you can. I mean, you can write things like this in the gospel type, and I mean you can also use like you need a new type of sequences. Okay, so you can provide this, and you can even write axioms about the new types, and so on and so on. So that you can introduce. Yeah, you can do things like these, and you can write operations on your new mathematical data types, and these will only be for this very specific case. These will only be visible on specification and not on the program.
And this won't be an algebraic data type.
I mean, you mean like this? That's it. You can. No problem.
My question is then how you translate this to separation logic predicates.
I'm not sure I follow your question. Are you thinking about some problem in particular?
Maybe I missed some point, as if I understand it, you translate your views and all pre and post conditions to separation logic formula.
Yeah. So in fact, the separation logic framework that we are using, you can encode algebraic data types. Because the language is equipped with the algebraic data types. In fact, is the separation logic that CFML is using. So you can encode algebraic data types. And I mean, you could also try to provide, even if you have defined your type like this. Now you could also give it a model, right? You could also give a model view to this algebraic data structure, and I mean, even the view could be an algebraic data structure, and that would still be fine, bearing in mind that this is the logic that CFML embeds inside Coq. So you have support for algebraic data types because it's a language that was already built with OCaml in mind.
Oh, thanks. I have another question on which is off the side of this talk. Actually, you said that you don't currently support generalized algebraic data types, and my question is, how do you plan to represent formulas on ADTs, because ADT language, first order language, is actually very inexpressive, and I wonder how you would represent, for example, invariants.
Yeah. So far, if you try to write a program using GADTs, Cameleer will scream saying no support for GT, so you cannot even continue with that. So we have actually thought about it, and we have a student that maybe is going to take that as a master research topic. The idea is that it actually involves a lot of work because of the equality that SMT solvers provide. So it's that the joke about the John Major equality, okay, or the polymorphic equality that you only get, for instance, in Coq. So first of all, you need to try to encode a very sophisticated type system inside Y3, and then you still need to use or to extend SMT solvers, the equality notion of SMT solvers, to deal with GADTs. So as a first step, before doing all of that immense research work, maybe we will try to translate that into Coq, because we are aware that inside the Tezos Foundation there is a tool called Coq of OCaml, okay, where you try to translate pure OCaml code into Coq, and they actually use GADTs and they generate a bunch of axioms. So maybe as a first step, we'll try to do as they do. But in the end, if you want full or mostly automated proofs of JDTs, you need a lot of research and extension work on Y3 and also on SMT solvers.
If we don't have any more, thank you very much for your presentation. It was very interesting.
Thank you for having me. It was really a pleasure.
Yeah. And maybe this was not the last time.
Yeah, I hope so.
Thank you very much. Goodbye.
Thank you. Bye.